Compressible Navier-Stokes.
Good morning. I had to take my child to daycare today and barely made it here in time. And I realized that no one realize what turbulence is until one has kids. And it helps if you live in Rio. But okay. So I'm going to talk about convergence of time averages and recurrence. So this is a bit of academic topic. And I realized during the course of the conference that this is a bit academic, and I decided to insert at the end of the talk a few more applied issues, and I mentioned at the end. So I made this part a little shorter and mention a few more things at the end. Okay, so this is, well, I'm going to talk about 3D Navier-Stokes equations mostly, incompressible Navier-Stokes equations, in the periodic boundary conditions with zero space average and or no slip boundary conditions, and the forcing term is a steady forcing term, just an autonomous case. And so just to set the notation, that's the classical notation. So I think all of you know here, but just to make sure that the age space is the L2 space with the divergence-free boundary condition and the appropriate boundary conditions in the case. V is the H1 space, and V prime is the dual space, the domain of the Stokes operator, and HW is the space H with the weak topology. And F, I will assume, lives in H in the steady case, as I said. So I'm going to talk mostly about statistical solution and things that derive from statistical solutions. They are associated with statistical solutions. So this is about recurrence and pointwise ergodic theorems. So these are related to invariant measures, and in this case it's about statistical solutions, which are related to invariant measures. So just to recall this, so the statistical solutions are in a sense the ensemble average from turbulence theory. So ensemble average in a rigorous sense. So Cecilia mentioned this in her talk, but I think that was the only talk. I'm missing Mike's talk. I don't know if he talked about this. I think that was the only talk, but just to recall, so usually you have differential equations, and those lines there are the solutions of the differential equations, and you can look at individual solutions, or you can look at the probability distribution of initial conditions and see how the probability evolves with time. And the statistical solutions are related to that, the evolution of the probability distribution of the state of the system. Okay, so if you have a well-posed system, the probability distribution is just the probability carried by the semi-group. If you don't have that, you have to define the statistical solution in some sense, and this is done for the Navier-Stokes equations. And there's a theory for that. This is the theory of statistical solution. I will mention more about this. And the stationary statistical solutions is the case when the statistics of the flow is stationary. So this picture illustrates one of this case. So you have a flow going upwards here, and there is smoke coming out from the left. And if you average this in some sense, this is a time average. It's a photograph with a long exposure, so this is a time average. And you see this picture here, which is stationary. If you wait a little bit and take another picture with a long exposure, you see the same picture. So this is an illustration of stationary statistics of the flow. And behind this, is a measure which is stationary. And so you can associate with that a stationary statistical solution. And so the stationary statistical solution, in a sense, they generalize the notion of invariant measures for dynamical systems, but in the case of a system that it's not known to be globally well-posed. So a natural academic question is what about the ergodic results? The theory from ergodic, the results from ergodic theory that are applied to invariant measures, can they be generalized to stationary statistical solutions? So that's the question that I want to address here. So in particular, one of them is what about the limit of invariant of time averages? So time average is very much used in turbulence theory, and from the classical theory of turbulence, and also for statistical for rigorous estimates, usually take an upper bound as supremum, a lim sup of time averages to get upper bound estimates, or lim inf to get lower bound estimates, but one never address whether this limit really exists or not. And for well-posed system, there is the Birkhoff pointwise ergodic theorem that says that this limit exists almost everywhere with respect to any invariant measure. So since we have stationary statistical solutions, we can ask, well, does this exist almost everywhere for stationary statistical solution with respect to stationary statistical solutions? And that's one of the questions. What about recurrence theorems too? And sojourn time, can estimate time that the solution recurs or comes back to some set of positive measure. So these are done for a globally well-posed system, but what about 3D Navier-Stokes equations? So the first one that I want to mention is the recurrence results. So this is the old result by Poincaré. So that's the statement over there, and this is a picture. So this drawing here is the support of an invariant measure, and let's say we take a set E, and so you got a positive measure. This is the part that is positive measure here. And you take a point X for almost every point in this set E. The trajectory comes back to this set infinitely often. Okay, so this part that is outside the set, the support has measure 0. So here, the orbit will not come back to this. It will just go to the measure, but it has measure 0. Okay, but inside here, the measure will come back very often. Okay. So there are some extensions of this result for some set valued dynamical system where you don't have uniqueness. You have existence, but you don't have uniqueness. So you start with the initial condition, but you can have several solutions. So you have a solution operator where you access the phase space. You start with a point, but you have a set of many states, possible future states, and you can, well, of course, you can start with not a single set, but with a whole set and go to several sets. And so there are some extensions of recurrence result to operators like this. I think the first one that I tracked is by Oban and this from Koska and Lasota. But they asked some very stringent conditions on the space and on the measure, and to get the recurrence. And for the Navier-Stokes equations, you don't have anything close to these conditions. Then there are many other results that follow along these lines here. And in particular, for this inequality here, what we seem to have for the Navier-Stokes is the opposite inequality. So it's what we call accretive. So the measure actually grows in time because of the non-uniqueness of backwards in time. But we managed to get some kind of recurrence. Yeah. No, well, we don't know that it's strictly larger. We can prove this for stationary statistical solutions.
We kind of think index needs to compute this P of X with, so is this a power set? He thinks it's probably probabilities or power set.
What?
P of X has this.
No, parts of X.
Powers of X. So
Parts of X. The collection.
it's not probabilities.
No, it's not probability. I'm sorry. This statement. Is, yeah. I have a picture and a photo slides, some slides down, and I might illustrate that. Yeah. So, and there's some issue with the definition of Leray-Hopf weak solutions that makes some difference in the way we handle this. And let me just make sure we clear this. So, well, the first three statements are classical. So it satisfies the Navier-Stokes equation in the weak sense. Satisfies the energy inequality. That's to be a Leray-Hopf weak solution. It has to have this regularity. And the last condition, it has to be strongly continuous at the origin. So this last condition, not everybody uses. For instance, George Sell doesn't use that, and this is, I think, in one of his books and some of his works on trajectory. He doesn't call trajectory attractors. I think he calls something else. But Babin and Vishik they call trajectory attractors, and he doesn't use this condition. And George Sell doesn't use that too, either. But in the beginning, I remember Foyas and always used this condition, and Ladichenskaya and some others use this, and this is important to get a priori estimates from the initial condition. Okay, so because of that condition, when you from this energy inequality in the distribution sense, when you integrate that, you get this estimate, but this is valid from starting point T prime, which holds only from points of strong continuity from the right for the solution U. So from the condition 4, you can take T prime equals to 0. So this allows you to get estimates from the initial condition, to get a priori estimates from the initial condition. That's why, well, it's good to have the condition 4 in the definition of the Leray-Hopf weak solution. It's also good that you can, this condition is also good because you can concatenate or paste two solutions together. So if you have two solutions, you can glue the two solutions and you form a larger solution. One bad thing with this condition is that you may lose compactness of the sets of solutions, or closedness of the set of solutions. And I think that's one reason why Sell and Babin removed this condition. And of course, and when they work with the trajectory, with the space of trajectories, they use the topology in that space, and then when they start with a bounded set, they use the bounded set there, so they don't use the bounded set. They don't start with a bounded set in the phase space. They start with a bounded set in the trajectory space. So they don't care about the a priori estimates from U0. The a priori estimates are from the whole, start from the bound from the whole solution. So they don't need this. And this also affects the solution operator. So if you look at this, if I define the solution operator in this way, so the P of H is the set of subsets of H, the parts of H. So I define sigma T of V as the states of U at time T of all the Leray-Hopf weak solutions that at time 0 started at the set E. Okay. So of course at time 0 that's just the identity in H. But I don't have a semigroup. Even in as a set valued operator, I don't have a semigroup. I have this inclusion here. Because if I take a whole solution like this, if I take a whole solution, this drawing is not very good, but anyway, if I take this part here and this part here as a whole solution and I break it like this might not be a solution because it might not be strongly continuous at this point. So this solution here might not be this solution pasted with this solution. So this might not be a solution in that sense. It might not be strongly continuous at this point. Okay, so this part might not be equal to this, but it might be just included in this one here. On the other hand, if I define it without the condition 4, it's missing here, without the last condition, then I get the opposite inclusion. Because I may not paste two solutions. If I start with a solution which is not strongly continuous at this point, and if I glued with another condition, with another solution, the two solutions combined may not be a weak solution. It's a weak solution, but it's not a Leray-Hopf weak solution. It might not be a Leray-Hopf weak solution because of the energy inequality. It may not satisfy the energy inequality. So I have this opposite inequality. So this doesn't seem to be a good way to define. I didn't work too much with this. I don't know if the recurrence works with this operator here. Yeah. Yeah, it's missing here. The condition of strong continuity at the initial point. At the initial point. So I cannot paste the two solutions to form a long solution. So I don't know if the recurrence works in this sense. Okay. So the recurrence that I'm going to prove actually is for, in a more general sense, the first result is for measures which are accretive for this solution operator sigma t. Then you can apply for the statistical solutions because they are accretive. So a measure mu is accretive if it satisfies this solution, this condition here. So the solution grows. So this is a picture that I wanted to illustrate. So let's say that these are two solutions that join here. So let's say we don't have backwards uniqueness. So you have two solutions that join at this point, and the measure mu is like a half here and half here, and here is just one. So it's like a delta convex combination of Dirac deltas. It's half here, and here they join. So it's just one here. And the set E is just this point. So the initial measure is 1/2, but that sigma t is this guy here, which is 1. So the measure grows. It's 1/2 here, but it's 1 here. So the measure grows. Then you can, so this with respect to the initial time. So if mu is accretive, then you can show that this happens. It's not trivial because well, usually if you have a well-defined semi-group, you don't have many problems of measurability. But here for the Navier-Stokes equation, there are some difficult issues, and you need to work a little bit to show that these sets are measurable, universally measurable, and to prove that this holds. And then a result by Foyas and Teman in 1975, they show that any stationary statistical solution obtained as generalized limits of time averages of Leray-Hopf weak solutions of the 3D and Navier-Stokes equations is accretive in this sense here. And then more recently we proved that any stationary statistical solutions projected from a time-invariant Vishik-Fursikov trajectory statistical solution is accretive. And this includes those solutions here. And then we, in a work in progress, we proved the recurrence from this one here. Actually, this is an old result, but we haven't finished the paper yet because it's a long paper with many things. So the recurrence is like this. So we start with an accretive measure in that sense. We start with a measurable set E. Then for mu almost every U0 in this set E, there exists a sequence of times Tn such that the evolution of this set, of this initial point U0, intersects with E for every n. And the reading of this is like this, because it's not a single trajectory that returns. Actually, you might have different trajectories. At time t1, you get one trajectory that returns. At time t2, there might be another trajectory that returns. At time t3, there might be another trajectory. That's the way to read here. There might not be the same trajectory. But that's what we managed to prove. The proof doesn't follow the usual proof of recurrence. The usual proof, you look actually backwards in time. You have a continuous, semi-continuous operator, and the pre-image brings Borel sets into Borel sets, and you look at pre-images and work with that. Here you look at forward image, and you have to do different things, and there are some measurability issues. It's more complicated, but it works. But more recently we improved this and got we got a much better result where we get the same trajectory to return, and to return very often, so that the time average is positive and actually converges. That's the other result that I want to mention. Going very slow. So the Vishik-Fursikov, so there is this other notion of statistical solution. This is the Vishik-Fursikov stationary statistical solution that we first work on the set of trajectories and then project it to the phase space. So it's a Borel probability measure in the trajectories and carried by the set of the Leray-Hopf weak solutions. So we work with the space of trajectories, weakly continuous functions in H, and the space U of Leray-Hopf weak solutions, strongly continuous at the initial time. So there is the problem that this space is not closed, but we can manage that. And there's these two operators that are important for us. The projection at time t, so just take the point, the value of u at time t, and the time shift, time translation, sigma t, that just translates u by time t. Okay, so this is a semi-group, classical semi-group in this trajectory space. And that's how we will recover the classical results of recurrence, of Birkhoff, von Neumann, all the classical results we can recover on here. And then we just need to translate and see that everything works on this framework and for these measures. So a Vishik-Fursikov trajectory statistical solution is a Borel probability measure on that space, which is carried by the Leray-Hopf solutions, just to make sense for the Navier-Stokes equations, and has some, and it's like mean kinetic energy is finite. So the mean kinetic energy is null infinity log. So this is just a drawing of the measure up there in trajectory space. And the Vishik-Fursikov statistical solution, so without a trajectory, it's just statistical solution, is just the family of time projections of this. So these are family of, so these are probability measures in the phase space. You just project them in the phase space at each time t. So you have this family. And in the stationary trajectory statistical solutions is when this measure is invariant for the semigroup sigma t, the time translation semigroup. And then when you project them, you get a single measure mu. It's independent of t, and that's the stationary statistical solution. So we proved that this is accretive in that sense, but so the recurrence works for this measure mu. But now we have this better result for applying the Birkhoff ergodic theorem to this measure. We just need to make sure that this works. So so we got this Vishik-Fursikov stationary trajectory statistical solution. We got a function phi. It's a bounded Borel measurable function. Then for rho almost every u Leray-Hopf solution, the following classical limit exists. So this follows from the ergodic, pointwise ergodic theorem. We just need to. So this has another way to interpret this in projection in the phase space. We just project to the phase space to get a phase space statistical solution. Then for rho 0, almost every initial condition u0, there exists a Leray-Hopf solution u that starts at u0 such that this limit exists. So there's one way to read in trajectory space and one way to read it in the phase space. And we just need to make sure that everything works. And we write this we just need to make sure that this is strongly measurable. The semigroup is a contraction in LP of rho, and the classical theorem works. And there's another nice consequence of this that this result here, you are given phi, and you want to know if this holds, and the results that this holds for almost every u. But there's another thing that is usually done, which is to fix u and vary phi and define a measure mu depending on u. And this is usually done through the generalized limit. So you fix u and vary phi, and this defines a measure mu associated with this, and this is the time average measure. And this always puzzled Feuillage and us, and Manley was always bothered with this generalized limit, and that this measure could depend on the generalized limit and was too obscure. And this result also actually showed that this is independent of the generalized limit, because actually this almost everywhere equal to the classical limit. So in a sense, this is independent of the generalized limit. But you need to be careful, because in one case you fix phi and vary u, and this one here you fix u and vary phi. But you can make things work, and you need to actually you want to show this U is for almost every, you fix phi and you get U for almost every U. So this is not good for a set of measures 0. For a fixed phi, this is not good for a set of measures 0. So actually, to make things work, what do? You want to work with a space of phi which is separable, and then you get a countable collection of phi, and then you get a set of measures 0 for each phi countable, and then you take an intersection and you still get a set of measures 0 working for every phi, and then that's dense in the set of all phi's, and then you are done. Then you make it work, and you get the two measures are 0 for every phi k in this set, in this dense set, and that's the idea. And that works because you can do that because these measures are carried by this set P of H, because they are time averages of weak solutions. Weak solutions are bounded by some R. They converge to the weak attractor. The weak attractor belongs to a bounded set in H. So in BH of R, you work with the weak topology. W should be inside. You work with the weak topology, and this space is separable, so you can get a countable collection phi k in this set here, and then you do, as I said, you work with a countable collection. And we also use that this space is separable and metrizable to show that this is equal if and only if the integrals are the same. So that's how you show that the time average measures are independent of the generalized limits. And I think I'll be brief on this, but if you take in the time average measure, if you take phi to be the characteristic function of a set E, then you get what's called the sojourn time. Right? So this time average here, you can read it in this case here. So this is the Lebesgue measure of the time of the set of times t where U of t belongs to E, and this is a relative measure of the time spent in the set E within the whole time t, and you take the whole time, the limit as t goes to infinity. So that's the mean sojourn time, the mean time the solution U spends within a time within a set E. So even if the trajectory returns infinitely often to E, to this set E, if it returns every once in a while, this limit can still be 0. But we can prove actually that this limit is positive if the measure of this set E is positive. And actually, we can show that this limit is positive for rho almost every initial condition. So it's much stronger result than the recurrence theorem. So I won't go. I think I have 5 minutes more. Okay, well, I think I'll be brief in this. But the result is that for rho almost U, all U in weak solutions, starting at a set E of positive measure, I forgot to say here, the sojourn time is well defined, and it's of positive time. So it returns to E very often, and so often that the average time, the mean sojourn time, is positive. So it's a much stronger recurrence time. And then there is a reading of this in phase space too. And for rho 0, almost all U0 in the set E, there exists a trajectory U starting U0 that returns infinitely often to E. Okay. And then there's a proof here, but I won't go through this. Okay. So these are some some of the results that I wanted to mention about recurrence, time averages in this line. And as I said, I wanted to move a little bit the subject and talk about more about some estimates. And actually, these are all the estimates. I just wanted to draw some attention to this and challenge you to this topic. One part is to challenge you to one thing, and the other is to draw attention to one result that I think is being overlooked. So this is the 3D periodic channel flow, so this is the Navier-Stokes equation driven by a pressure gradient and a periodic channel, and so these are the essential quantities here: the enstrophy dissipation rate, the mean longitudinal velocity, the skin friction coefficient, the Reynolds number. And this is a result of constant enduring, essentially the main idea, and we just made a slight improvement that's not really important. The main thing is in Charlie and Peter, and essentially got an estimate for the skin friction coefficient, an upper bound from below, a lower bound and an upper bound, physical upper bound. And the lower bound is for the Poiseuille flow, and the upper bound is the turbulent, what's expected for the turbulent flow. And what I want to draw the attention is that all these estimates have this problem. Most of these estimates have this problem. You get this estimate that is a very large range because they are good for. You can do this for time averages or for ensemble averages. Doesn't matter, but you don't see the turbulence there, right? It's a wide range of estimates that you do, and for the statistical estimates, for instance, you claim that the statistical estimates do that because they model turbulent flows, but the estimates at the end don't see if the statistical solution that you are estimating is carried on a direct solution that's just a laminar flow or really a turbulent flow. They don't see that. All the estimates that you do, you don't see that. So you get the lower bound. That could be just a Poiseuille flow or that. And the challenge, I think, that no one is really working on this, and I think we need to work this, is to characterize the statistical solutions or whatever, or the solutions in some sense, they are turbulent. I think we need to work on that to get sharper estimates that are closer to this. So to give characterizations of turbulent measures that maximize or minimize some quantities that yield Kolmogorov or Kragner spectrum or anything, physical quantities that are related to this thing. And on the opposite direction, there is the Poiseuille flow. For the 2D channel flow, for instance, the Poiseuille flow minimizes the entropy dissipation and maximizes the energy dissipation. But we need to do something for turbulent flows. Can you say that the turbulent flow maximizes or minimizes something? That's what we need to do. And something along the lines of the 3D energy cascade results. This is something along these lines, but we need to go further than this. So this result, node result now that say at the end that if this kappa tau, which is a Taylor-like wave number, which is a mean, which is this wave number here, which is essentially the Taylor wave number. If this wave number is much larger than the wave number where you are forcing your flow, so the flow is forced up to some wave numbers, then you get an energy cascade. So this is essentially the energy flux, and so this essentially says that if the wave number, if the Taylor wave number is much larger than the forcing wave number, then the energy flux is comparable to the entropy, to the mean energy dissipation rate among within some energy, supposedly energy cascade range. So this is some kind of characterization, but we need to go much further than this. And we have something similar for the entropy cascade. So this is the challenge. And the other, so we need to go further than this and along the direction of that to characterize turbulent flows. And this is the other thing that I wanted to mention that has been overlooked, and I just wanted to draw the attention. It is in 2D, we say that the entropy dominates the energy for the cascade, and that's why the Craihan spectrum, you see the Craihan spectrum and not something like the energy spectrum. And there is one estimate that we got some time ago. I forgot to give credits here. And that was 2003, I think. Fayaz, Mali, Mike, and I, 2003, I think. And so for the entropy cascade, we look at the entropy flux, and throughout a certain range of wave numbers above the forcing number, the entropy flux should be a cascade, should be comparable with the entropy flux along that. So it should not decay, it should be constant energy flux along those wave numbers. And the energy cascade, if you had an energy cascade, those should be comparable too. So it has a cascade, right? And the way to see that they are constant is to look at this quantity here. So these are almost the same if this quantity is small. And the way to see if this is stronger than this is to prove that this ratio is small. And then we compare this ratio here, and we prove that this ratio is smaller than this. And then if kappa sigma, which is like a Taylor wave numbers, but for 2D, if kappa sigma is much bigger than the highest forcing wave number for F, then the entropy cascade dominates the energy cascade, and that supports the Craihan wave number. So I just wanted to draw attention to this estimate, which I think is very nice. And it's a rigorous estimate that supports the Craihan spectrum and it's been overlooked. So with this, I finish my talk.